go. All right. So we are done with binary comparison, I think. So this is one thing you can also do. Okay, some of you can, kind of do this too, is to go to the website, just go through the video like shortly before the class and try to remember what we talked about in the previous class. So the previous class is the one on Monday, which is this one here. So I can go straight to the end and figure out what I talked about on that day, right? So we can go. I spent a lot of time talking about VSP, which I think is kind of important. But we did talk about everything that we need to talk about in binary comparison. So in today's class, we can move forward to talk about floating point numbers. Unless you guys have specific questions about binary comparison or any topic, up to that point. So are there any questions about binary comparison, binary subtraction, signed versus unsigned interpretation, binary addition, base conversion, or any one of those topics that we have gone over already in this class? Okay, and not seeing any questions. All right, excellent. So that means we are ready to move forward to floating point numbers. So when I talk about floating point numbers in the past, it was kind of a challenge to find out why people need to understand floating point numbers, other than I think it's an important concept, but it's hard for me to find out to tell people why it is important. But these days, it is actually pretty easy. The reason why floating point numbers become kind of increasingly important is because of AI, because of LLMs and neural networks. Because when they say, oh, this particular model has, X number of parameters, what is a parameter? A weight, exactly. And the way we represent a weight is to use a floating point number. So but why is it important? Because if you can figure out a faster way to perform multiplication and addition with floating point numbers, you will be employed. Okay, you'll be super valuable because all these semiconductor companies, Nvidia, AMD, and now Qualcomm, they're all looking for more efficient ways to do multiplication and addition with floating point numbers. Okay, so that adds relevancy to the discussion of floating point numbers. All right, so with that said, before we get into binary floating point numbers, we'll go through some base 10 examples as usual. Okay, so we'll start with things that we probably should know. Okay, if not, we can definitely, kind of introduce those concepts. Okay, so how many people know what this is representing in C++ syntax? In other words, if you are to say C out, okay, less than 3E8, what is the compiler or what is the computer going to output? What is the value being specified when you say 3E8? 300 million. Okay, very good. Because 3 is what we call the coefficient. E is really just a separator between the coefficient and the exponent of 10. And 8 in this case is the exponent of 10. So that means E, a 3E8 is actually specifying the following quantity, 3 times 10 to the power of 8, which turns out to be 300 million, which is also the number of meter per second of the light of speed, or approximately. Close enough. Okay. Are we okay so far with this is called the scientific notation. So we're good? All right. So it can specify really huge numbers without using a lot of zeros, because if I were to use a bunch of zeros, it will be 3 followed by 8 zeros. 1, 2, 1, 2, 3, 1, 2, 3. Okay. So I think that illustrates why 3E8 is a slightly better notation. Okay, but it can also go small. Okay, in other words, if you look at the size of a transistor these days, so with the M4 chip, that Apples are using, what is the transistor size of an M4 chip? Okay, this is a computer science class. We can use Google search. What is the transistor size of the M4 chip? No, no, no. But I'm not asking about the number. I'm asking about the size. So the second generation is a 3 nanometer process. Okay. So now the question is, if I want to specify 3 nanometer in meters, what is the number? So that would be 3 times 10 to the power of what? What is a nano? Okay. You have to come up with all the SI units. Okay. They usually go by 3. So a milli is 10 to the power of negative 3. A micro is 10 to the power of negative 6. So a nano is 10 to the power of negative 9. Okay. So that means I can use 3e negative 9 to specify 3 nano. Okay. But if I want to express it in the full format, it'll be 3 times 10 to the power of negative 9. But if I want to use the decimal representation, it'll be I have to count zeros because in this case I have exactly 8 zeros and then the 3 is all the way to the end. So we have 1, 2, 3, 4, 1, 2, 3, 4, and then the 3. Okay, so I think we are starting to see the usefulness of the scientific notation. We can specify really, really large values and we can specify really, really small values. When I say small, it doesn't mean it's very negative. It means it's very close to zero. Okay. So we can specify gigantic values, for astronomy classes. We can specify really small values for chemistry classes too. So because in chemistry, sometimes we have to measure or specify EV, okay, which is not an electric vehicle. It is the charge of a single electron. That's a really small number. We also have to specify mole, which is a really big number. Okay, it's the number of molecules in it's basically it's a count of the number of molecules for a particular chemical. Okay, so and in neural networks, we also have these values to specify each parameter. So are we having a good handle on scientific notation, but in base 10? We good? All right. So now we kind of shift our attention to binary numbers or how we represent values in base 2. So we'll start with something that we should be fairly familiar with, okay? So let's say 27 point, I don't want to use the same example as what I did yesterday, so I want to use maybe 875 this time, okay? This is a base 10 number. So the first thing I want to do is to convert the value of 27.875 in base 10 to a binary number. Okay, so whatever follows this is kind of something that we should know already, but I'm going to go through this whole process just so that you guys go like, oh, okay, now I remember how to convert a number into base 2. So if you're not familiar with conversion to base 2, like you cannot really remember all the powers, I would say just kind of make a little list here of all the powers of 2. But since this one also go to the fractional side, I would also include zero point 0.5, 0.25, and then 0.125. And if you want to go smaller, that's okay too, but I don't think we need that in this case. So now that we have the powers of 2, then we just start with the larger ones, and then we go from the larger ones to the smaller one. The nice thing about base 2 is either you have or you don't have one of the powers of 2. You never have 2 or 3 or any other number of a power of 2. Because when you're dealing with base 7 or base 8 or base 10, there's a division process involved and it's kind of time consuming. But in base 2, it's either yes, you have it or you don't have it. Okay, so it's just comparison. So when you look at 27.875, I think we got a 16. And after the 16, we definitely have an 8. After the 8, we have a 2 and a 1. I'm just double checking my math here. Yep, okay. And then after that, we do have a zero point 0.5 and we have a 0.25. We also have a 0.125. Is that okay? So This process does not have anything to do with me being a computer science person. It really just has to do with I can do mental math relatively fast. Okay, I'm not even going to pretend that I'm fast. Okay, there are competitions where people do, I cannot even remember, ungodly number of digits by ungodly number of digits, and they can do everything mentally. I have no idea how they do it, and I don't care. It to me, I know this is going to sound really bad for people who practice a lot to win those competition, but to me, it really sounds like a waste of neurons in our head. Okay, because if machines can do the computations a whole lot faster with high precision, why do you waste your brain to do stuff like that? Okay, now this, on the other hand, is something that is kind of important because I want to illustrate the process. Okay, so now what do? We say, okay, this is the 16 is 1 followed by 4 zeros in base 2. Okay, the 8 is 1 followed by 3 zeros in base 2. We don't have a 4. The 2 is 1 0 in base 2. The 1 is, guess what? 1 is base 2. And then the point 0.5 is point 0.1 in base 2. The 0.25 is 0.01 in base 2. And then the 0.125, the 1/8, is 0.001 in base 2. So when you add up all of these, then we have 111, oops, 11011.111 in base 2. So that's how we can represent what we see in base 10 as 27.875 into the binary representation of 11011.111 in base 2. So do we have any questions about this? Okay, so I'm going to pick one digit just so that we understand what is that doing here? Okay, so I'm going to pick one of the digits and ask, what is this guy doing here? Okay, it is telling us that we have one of 2 to the power of negative 2. Now, how do we know it is corresponding to digit negative 2? Because the dot, the decimal point, is telling us where we can find digit 0. Whatever is to the left-hand side would be increasing the position number. Whatever is on the right-hand side is decreasing the digit number. So that makes this one digit negative 1, and this is now our digit negative 2. The position of the digit tells us which power of 2 is this digit telling us about the quantity. Okay, so that means the one that is highlighted, which is under the cursor, the mouse cursor right now, is telling us that we have one of 2 to the power of negative 2, which otherwise to us is known as a quarter. So are we good so far with how to read a binary number even though it has decimal places? Okay, all right. So now we look at this number, and if I were to make another equality statement and go like, um, this whole thing times 2 to the power of 0. Would anyone object to this equality? What is 2 to the power of 0? It's just 1, okay? Multiplying anything by 1, you just get whatever you started off with, so it's not a big deal. So now I'm going to ask you this question, okay? What if I were to shift the binary point? Yeah, I know it's called a decimal point, but this is a binary number, so it's kind of odd to call the point a decimal point when it is in a binary number. So I'm going to call this one the binary point, okay? So what if I were to move that point over to the left-hand side by 1 place? Okay, so take it away from here and put it here instead. What do I need to do in terms of the power of 2 in order for this equality to hold true? So the way you think about this is you think about the digit positions, okay? So let me use the mouse pointer. So this is also getting recorded. Well, let me explain the whole thing first. This was our digit 0. The very same thing is now digit negative 1. This was digit 1. It now becomes my digit 0. So if you think about the quantity that was represented by only this portion, comparing that to what it is representing now, what is the change? How would you describe that change? It is decreased, but be more precise about how it is decreased. Not tenth, we're dealing with binary numbers, but you're close. Okay, but but what is the percentage of the decrease? Sorry? No. Okay, what used to be digit 0 is now digit -1. What used to be digit 1 is now digit 0, and so on. So remind me again, okay, remind me again what quantity is associated with digit 0? 1. What quantity is associated with digit -1? 1/2. So that means all the powers of 2 that are being specified, they are now 1/2 of what they used to be. Which also means when you look at the value represented by 1101.1111, it is 1/2 of the value represented by 11011.111 as a base 2 number. No, because we need to compensate, right? This value is 1/2 of what it used to be. I have to multiply the whole thing by 2 in order to maintain the equality. Because one side is 1/2 of what it used to be. In order to maintain the same value, I have to now say, oh, okay, multiply that thing to 2 so that we are maintaining the same value. Is that okay? It is the same thing that you can do in base 10. Okay, so if you're having some problem understanding this in base 2, we can do it in base 10. Okay, so let's go ahead and do this similar thing in base 10. So let's just say I have 68.79 in base 10. Okay, I want to maintain this equality, but on one side I say, okay, 6.879. What do I need to multiply to 6.879 in order to end up with 68.79? Multiply by 10. Because the moment I shift the decimal point, this one is decimal point, to the left-hand side, the new value is only 1/10 of what it used to be. But why 1/10? Because base 10, because it is base 10. Okay, every digit represents the quantity of a power of 10. By moving that decimal point to the left-hand side, the power of 10, they all got decremented. The power got decremented by 1, which means each digit is now specifying the quantity of 1/10 of what it used to be. Is that making any sense? Okay, so this is the same thing except it's base 2. Okay, so I can keep doing this, right? So I can now go like, okay, so if I want to do the whole thing so that it becomes 1.1011111 in base 2, so I'm skipping a few steps intentionally, but I want you to tell me what would be the power of 2 in this case. Very good. So it is 4 because I just skipped 1. Okay, so now it's 2 to the power 4. Does that look like scientific notation to you? It is a scientific notation. We have a coefficient times whatever base to a particular power. It is scientific notation. So that means, oh, okay, so the whole concept of scientific notation, which means we have a coefficient multiplied by a power of whatever base we're dealing with, that's the whole idea of a scientific notation. It works in base 10, it works in base 2 too. Are we good with that concept? So for those of you who think, oh, Tech, you're pulling the same boring trick again by starting with a concrete example and then somehow turning it into something that is a little bit more general and then re-specify it into a specific base. Yes, I just pulled the same trick again. And if you're bored, I apologize. All right. So what why is this even important? This is important because now we go like, well, what if we have really gigantic values that we need to specify more than 2 to the power of 64, okay? And then we have tiny little amounts that are really close to zero that we also need to specify. We can't really use unsigned for that, okay? We cannot use int, we cannot use unsigned, so we have to use double, okay? So have you guys come across the type double, double, in CISP 360? All right, excellent. So what is it representing? What double of what, right? That's always kind of my question is double, but it's doubling what? Well, as it turns out, double is really just the abbreviation of, okay, I'm going to spell it out here, IEEE double precision floating point, whoops, floating point number format. That is the full name or almost full name of double, because now people ask, what is IEEE? What is IEEE? Okay. So let me see if I can remember that. Okay, this is how my brain works. So I think it has to do with electrical and electronic engineer. So that's the EEE side, engineer. The I part, I think it is International Society of, okay, there are some words that are not spelled out here, or institution. I think that's institution. Institution of Electrical and Electronic Engineers. Okay, so my brain just kind of pieced everything back together by looking at the individual pieces. So we'll take a look. Okay. So the best way to look at this up is really just to look into Google and ask for what is the double. Okay, double as a type, floating point. Okay, that should be enough. There we go. So now we go to Wikipedia and it specifies this is the IEEE 754 standard, which has its own huge, gigantic document. But it does mention what is IEEE, the Institute of Electrical and Electronics Engineers. So I was able to piece everything back together, because my memory is really poor, okay? But I can understand things, so I can use my understanding of things to make up for the lack of memory precision. In other words, if you guys were to ask me, Tag, can you just repeat what you said in the previous sentence? I go like, I cannot. Not because I don't want to, but because I really cannot remember what I said. Once the words come out of my mouth, it's not in my brain anymore, so I cannot remember any one of those. That is how my brain works, or not work in some cases. All right, so what exactly is double? Okay, what is this? You go, oh, okay, here we go. We like equations. Okay, so this is the equation to describe, how to interpret the bits. Okay, I looked at this and go like, not the best way to describe it. And that's why I have my own. So I have my own, which is completely self-sufficient, and it uses the notation that we have been using in this class. Okay, so the actual definition, okay, you can start with this part here, but it really boils down to this entire thing here. So everything from this open paren all the way to the end is specifying the double interpretation, or this is the value of the double interpretation of a bit pattern that we call F. And F has 64 bits. Is that okay? So this is kind of consistent with the notation of VS, VU, right? So this is really just an interpretation. What is the value being represented by the bit pattern that we call F? And there are 64 bits in F. All right. So now we take a look at this gigantic, kind of clumsy formula here. And then we ask, okay, tell me what that is. Well, what do you think it is? Yep. So F. What is F63? What is what is only this part, okay? If we just focus on f subscript 63, using the convention that we have been using for addition, subtraction, comparison, and all kinds of stuff like that, what is that referring to? Mm, is Yes, it is looking at bit 63, but since f only has 64 bits, it is also called the most significant bit. Well, not yet. We'll get to that part. Okay, so right now we just look at F63 and we say, oh, okay, so that means the bit at position 63 of the bit pattern F. Have we been using this kind of notation? Okay, because we have been using this kind of notation for x plus y equals to s and so on and so forth. So this is not new. And it also has its own little description up here, which also kind of talk about what f is. Okay, so f is just a bit pattern. All right, so this is easy. Okay, if f of 63, if the most significant bit is a 1, then the entire quantity is positive or negative. If f63 is a 1, is it specifying positive or a negative amount? Negative, that is correct, because negative 1 to the power of 1 is just negative 1. If f63 is a 0, then it's specifying a non-negative amount. Okay, very good. So now we look at this part here and go like, whoa, this is too much. I can't handle this. You can't handle it. You just have to spend some time, okay, and just kind of go through the whole thing. And the best way to read something like this is substitution. In other words, you just say, okay, what happens when I equals to negative 52? What are we talking about here? When I equals to negative 52, then we are looking at f of 0. Okay, f of 0 is the least significant bit of f. Okay, but at the end of the day, it is just either 0 or 1. So now the question is, well, it's a 0 or 1 of what? 2 to the power of I. But I is negative 52, so that means bit 0 of f tells me the absence or the presence of 2 to the power of negative 52. Tiny little amount, okay? The next digit, f of 1, tells me whether we have a presence or the absence of 2 to the power of negative 51, and so on. So you just go all the way to what if I equals to negative 1? Work it out. F of 51 is telling me the presence or the absence of 2 to the power of negative 1, which is a half. So that means, oh, okay, so we are really just looking at 1 plus a bunch of negative powers or the absence or the presence of a bunch of negative powers of 2. Is that okay? Yep. Yes. Yep. Yep. The sigma is representing the quantity that is specified by all the digits to the right hand side of the binary point in the base 2 representation. Mm, it's a binary number. The fractional. Yeah, the fractional. Yep, the fractional. Yep. Yep. To the right hand side of the dot. Yep. Um, so the 1 plus is constant. In other words, this 1 does not depend on any one of the bits of f, which leads to a little bit of a problem because now we cannot represent 0 because this one is always there. Okay, we can get pretty close to 0, but never really exactly 0. So we'll handle that situation in just a little bit. So this one is always here. This is the fractional part of the coefficient. Is that okay? So if I relay this back to what we have done already here, this 1 plus is accounting for this one over here. This sigma here is accounting for all the things to the right-hand side of the point. So all of these digits is basically specifying what the sigma is going to compute to. Question? Correct. So in this case, we just have a whole bunch of implicit zeros all the way down. So that means, we do have a 1 for f of 51, a 0 for f of 50. Okay, wait, am I doing this correctly? Yep. Okay. So we have a 1 for f of 51. We have a 0 for f of 50. We have another one for f of 49, and so on. Is that good so far? Because I can pick a particular one up and know exactly which digit it has to correspond to. Let's say we're talking about this one, okay? So when you look at this one, you ask, which digit is this? This is digit 0, -1, -2, -3, -4, -5. This is -6. So if you want I to be -6, then what digit are we talking about? 52 plus -6 is 46. So we know that this one that is being highlighted right now is going to correspond to bit 46 of the floating point bit pattern. Is that okay? Maybe? Okay. So I will give you more examples, okay, in the conversion process. So for now, I hope up to this point we are still understanding, what the equations is specifying. Yep, yep. Not intentionally. All right. Yep. Why? Oh, because this is the format that IEEE decides to use. In other words, you have 64 bits within the bit pattern. Now you have to designate, okay, which one do we want to use to indicate the sign of the entire value, and then which part is going to specify the exponent of 2, and which part is going to specify the fractional part of the mantissa, which is the coefficient. So IEEE just decides, okay, we're going to dedicate 52 digits to specify the fractional part of the mantissa. Would be between the sign, which is bit 63, and also the exponent, which we'll talk about next. All right. So, okay. So right now we can see a one-to-one correspondence. This is called the mantissa, and it is being specified by this entire expression, including the 1 plus. Okay. So what about the power of 2? Well, in this case, our power of 2 is supposed to be 4, but the 4 is specified by this big mess here. Okay, so let's take a look at that big mess and find out, okay, exactly what is it specifying. So we're going to use the same trick, which is, oh, what happens when I equals to 0? When I equals to 0, then we have 2 to the power of 0, which is telling me the number of ones. Which digit is corresponding to it? It's digit 52. So 52 tells me the number of ones, digit 53 tells me the number of twos, and so on. We add them up, okay? And then what do? We subtract 1023 from it. Because if you look at the sigma notation here, it can only give us a non-negative value. It can be 0, but it has to be non-negative, right? Because it only involves addition. So what if I want to specify 2 to the power some kind of negative value? So IEEE decides to use a biased approach, which means we have a bias of 1023. Why they choose 1023 and not 1024, I do not know. I wasn't in that meeting. But they have chosen 1023 to be the bias. Okay, so in this specific case, we need to specify 2 to the power of 4. So that means this portion here has to specify a value of 4, which also means the sigma itself has to specify a value of 1027. That is correct. So that means I need to somehow specify 1027, because that's just this portion here, using 11 bits. Because from digit 52 to digit 62, there are 11 digits. Is that okay? All right. So getting back to this expression here, when you first look at something like this, you might think, oh man, this is really complicated. Well, maybe it is complicated, maybe it's tedious. You have to break it down into the smaller components and then understand it. Instead of looking at it and go like, okay, I'm giving up. This is way too much for me. Nope, it's not way too much for you. Are we doing okay so far? Because I'm trying to talk about the what is the attitude when we look at something that seems to be really complicated, but it really is not complicated. All it is involving is sigma, which is addition. It is looking at one particular bit and multiply that bit to a certain power of 2, add a bunch of stuff together, and that's it. Okay? So it is not complicated. It is really just, okay, I'm going to spend the time to find out what we are doing with this bit over here, what we're going to do with this bit, and then this entire group of bits, they together is doing this. They're specifying this amount. What are we doing with that amount? Okay? This amount is the coefficient. This amount is the biased exponent. But once you subtract the 1023, it becomes the actual exponent of 2 that we have to multiply to the coefficient. Okay, so that's my approach of looking at things. Okay, you break it down to smaller and smaller chunks, and also use different ways to try to understand how everything connects. Are we good so far? Good, good. All right. So this is a good time to tell you something that some of you will go like, "Oh, you should have told me at the beginning of the semester." And some people will go like, "Yeah, I knew this all along." Nothing, none of the knowledge that you gain in this class in CISP 400, 430, and 440 is directly applicable when you are hired, if you are hired. Okay? So you go like, "What is the whole point of going to college then?" What do you think? Exactly, to learn how to learn, okay? Because your job is to learn how to learn. My job is to is to do my job to the point where I don't have a job anymore, okay? So at the end of a semester, or when you get out of here, or when you get a degree in computer science, and you go like, I don't need a professor anymore. I don't need a stinking tech anymore to learn anything new because I know how to do that by myself. Well, come back to me and I will give you a pat on your back and go like, good job. Okay. Because that is what you need in industry these days. Hmm? Yeah, yeah. Instead of paying you, some $200,000, we'll just give you a pat on the back and go like, "Yep, this is your paycheck." There's unpaid internship. Even to get an internship, which used to be relatively easy, even that is getting difficult now because so many people realize, oh, I need an internship to get a chance to get a job. So getting an internship is also very competitive now. Okay. So that's something that I probably should have said at the beginning of the semester. I think I conveyed something like that at the beginning of the semester, but learning how to learn, which is how do you break down something that looks complicated, what attitude is healthy when you look at something like this and go like, okay, I can figure this out. Okay, I can break it down and figure this out instead of going like, I have no idea what it is, doesn't seem useful to me. I'm just gonna bypass this whole topic. You know, so. Hmm? Oh, everything is, I mean, you don't have to actually know this stuff, okay? Because the moment you say double x in C++, multiplication, addition, subtraction, everything is already handled, okay? the mentality of, I don't need to know this used to be okay. Okay, used to be like, why do I want to reinvent the wheel when the wheel is already around? But the thing about reinventing the wheel is not about the product, it is about the process. It is the process that is becoming more useful than the actual product. Yep, go ahead. It's the language, right? We are talking about power. Yep. hmm And it's also true. But even to date, I still do not know how to do that, teaching online 100% asynchronously. I still do not know how to do that. All right. Do we have, so getting back to this topic here, do we have any questions about how the example that we have here relates to this gigantic formula that is presented here? Are we good with that? Okay. So in the remaining amount of time, I'm going to do the conversion. In other words, I will come up with all 64 bits that is corresponding to the value, which is, let's make this a little bit more interesting. Let's look at negative 27, okay, negative 27.875. So now we want to figure out all the bits, okay? So we are doing the whole thing kind of in a reverse order now. Okay. We end up with, we know what it is supposed to represent. So in other words, we know the VD of F is negative 27.875. We are reversing back to like, okay, what is F63? What about the exponent bits over here? What about the fractional part of the mantissa? So we're going backwards, okay, to kind of go like, okay, how do we do this? All right, so we'll work with F63 first. Okay, what should that be? We are trying to specify a negative quantity here and seeing how f of 63 is used as a power of negative 1. What should it be? Should be a 1. Okay, very good. So now we look at this, awful thing here, and we know it is supposed to be 4. Okay, so now we go like, okay, so what is the exponent portion? In other words, if I look at the range of bits from bit 63, 62, all the way down to bit 52, what should that be? Well, whatever unsigned number it is representing using this particular sigma notation, it should be 1027, because we have to subtract 1023 from that in order to specify an exponent of 4. So that means to use our, oh, I can't really use that, sorry. So, uh, mm, 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 sort of. So, okay, I'm debating whether to use this notation or not. We'll go ahead and do it. So we are looking at the unsigned number, which is consisting only from bit 52 to bit 62 of the 64-bit F, and we interpret all 11 bits out of this. That should specify 1027. Are we okay with this notation? If we look at bit 53, sorry, if we look at bit 52 to bit 62 as if it is its own unsigned integer and interpret all 11 digits of it, I want to get the value of 1027. Is that okay? All right. So now the question is, what does it look like? Okay, if this is what we need, what would be the bit pattern of bit 62 down to bit 52 of F? So you go like, okay, we need 1024, which is the power of 2, and then it's pretty easy after that, plus 2 plus 1. So this is 2 to the power of 10, which means it's 1 followed by 10 zeros. So we'll give it 8 because we need a 1 for the 2 and 1 for the 1. So that's what it is. Okay, so bit 62 down to 52 would be 1 followed by 8 zeros and then 1 1 in base 2. Are we good with that? Do we understand why we need 1027 instead of 4? Okay. And then 2, do we understand how we go through that conversion? 1027 in base 10 is 1, 8 zeros, and then 1, 1 in base 2 because it consists of 1024 plus 2 plus 1. So we good with that? Yes. Okay. All right. So now what is left for us to specify? Okay. So now we look at f of 51 down to 0, okay, which is the rest of the 52 bits of the 64-bit pattern. So we are now talking about this portion here. Oops, sorry, I take it back. We are now talking about this portion here. All right, so according to our conversion earlier, do we have a half? Okay, so let me just go ahead and copy this. Okay, um, down here. All right, there we go. So do we have a half? Yes, we have a half. So that means f of 51 should be a 1. Do we have a quarter? Nope, we do not have a quarter. So f of 50 should be a 0. And then we just go like, okay, it looks like we are just copying all these bits down here. So, and then the rest, all zeros, bunch of zeros. So this is how we figure out bit 51 all the way down to bit 0. It's really just the fractional part of our mantissa. The term mantissa means it is a coefficient, but it also meets a special requirement. It has to be greater than or equal to 1, but it also has to be less than 2 when we're dealing with base 2 numbers. So is this value greater than or equal to 1? This value over here? Yes. Is it going to be less than 2? Yes. Because what does 2 look like in binary? 1, 0. That's right. So anything that is 1 point whatever is going to be less than 2. Now, can it get really close to 2? Yes, but it can never be 2. All right, so that means we have just figured out every single digit of the 64-bit bit pattern. So to rewrite the entire thing, we have a 1 for F63 because the value is negative. And then we have 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1 for the biased exponent, because this amount specifies 1027, but because there's a bias of 1023, so eventually the actual power of 2 is really just 4, which is 1027, this number minus 1023. And then the rest of it, okay, is really just whatever we have, as the fractional part of the coefficient or mantissa, which is this part here. So now we have specified all 64 bits. So are you guys just gonna go like, well, if text said it is, it is? No. So we want to be able to prove it, right? So how do we prove it? How do we prove that this particular 64-bit pattern actually represent, when interpreted as a double, will give you the value of negative 27.875? Okay, so we'll do this step by step. Okay, this does involve a little bit of a tricky thing. Okay, so I don't think I can expect you guys to be able to come up with this way of proving it. But once I explain it, I think you should understand the steps. Okay, so making connections between the steps is one thing, but understanding how the steps together work is a whole different thing. Okay, so the first thing we'll do is to combine all of these digits into one big huge mess without the spaces, like that. Okay, you go like, ugh, this looks awful. And this is the problem with binary numbers is, you need a lot of digits to specify anything. So what we'll do is we'll go like, yeah, I don't want to enter this base 2 number into any program that can help me verify this is actually the value that we need. Instead, I'm going to use base 16 or hexadecimal numbers. So base 16 is a really useful base. So I'm gonna give you a table here. You might want to write it down, or if you already know this, you can also just go like, okay, I got it. Or you can look it up online. Okay, the base 2 to base 16 conversion table is just like, oh, okay, 4 digits, all zeros in base 2 is 0 in base 16. Is anyone going to object that? 0001 is just 1. 0010 is 2. 0011 is 3. 0100 is 4. So I think you can probably complete this table all the way up to at least 9. Okay, but I'll do it for you. Okay, 0110 is a 6. 0111 is a 7. 1000 is a 8. 1001 is a 9. Okay. 1010 is a 10. No, it is not a 10 because the way we write a 10 is 10. But 10 in base 16 is representing what? No, no. Okay, let's think about this. This is going back to how we interpret numbers. Okay, so we are looking at a number that is 10, but it is in base 16. Are we good so far? So the 0 is telling us how many ones do we have, because 1 is 16 to the power of 0. The 1 is telling us how many 16 to the power of 1 do we have. In other words, 10 in base 16 specifies the quantity of 16. Just like 10 in base 2 is a 2, 10 in base 10 is a 10, 10 in base 16 is 16 itself. Is that okay? So that means I cannot use 10 here because I don't want to specify the quantity of 16. So the way we do this is we borrow from the alphabet. We borrow from the English alphabet. So this is A, this is B, this is C, D, E, and this is F. These are the 16 digits in base 16. Now, have we encountered a whole string of 0 to 9 and then A to F, in our daily lives? Well, the answer is yes. Okay. In fact, you can use your phone. Okay. I don't know how to do it in iOS. Pretty sure you can do it. I just don't know how to do it. But in Android, you can go to your connections and then go to, nope, not here. But you can actually get to the MAC address of your Wi-Fi, card in your phone. So when you get there, okay, let me see. Is it status? Status information. Yep. Okay, so it is status information. It will tell you about your IP address. In IPv6, it is in hexadecimal. It will also tell you your MAC address, which is the unique ID of your Wi-Fi connector. That is also in hexadecimal. So hexadecimal is already used in not only computer science or computer engineering, it is also used in networking. Okay, a lot of aspect in computer related fields make use of base 16 numbers, which is what we just talked about. So the way about converting from base 2 to base 16 is really easy. You chop the base 2 number into chunks of 4, and then you look up the table. So that means we just have to break it here, break it here, break it here, 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 and the rest are all zeros, so I don't really need to break them. So now we can look up the table and go like, oh, this is C, this is a 0, this is a 3, this is a B, and this is an E, and the rest are all zeros. Okay, so do we understand the conversion from base 2 to base 16? Groups of 4 converted, group of 4 converted, and so on. There's no division involved. Yep. Yep. A single. If you think of it, if you think about the number as a slot machine, each digit is one particular thing that rolls around. And I want that one thing in that window to be able to specify what we know as 13. So we cannot write 1, 3 because that would take up two slots. So we need to find a way to only use one character to represent 13. And computer science people just decided, okay, we're just going to borrow the first six characters from the English alphabet, A, B, C, D, E, F. So that A represents 10 and so on. So D is our 13. So is that making any sense? Because in base 10, a digit can only go from 0 to 9. In base 8, a digit can only go from 0 to 7 because all the digits can only go from 0 to the base minus 1. Now, with base 7, base 2, base 8, and so on, we have a different problem because we go like, oh, what about 9? Okay, oh, 9 requires two digits now. But when we get to base 16 and also base 64, the problem is um, I can go from 0 to 9, and then what? What is going to represent the quantity of 10, but only using one single character, because that's how we read numbers. Every slot gives you the quantity of whatever base to the power that is corresponding to the position. So we need one character to represent, in this case, 10, 11, 13, 14, and 15. So base 64 is a real thing. And the way they convert, you can look it up too. So you can look up, base 64. So base 64, encode and decode. Well, this is a tool to do the encoding and decoding, but you can also look up the alphabet. So they use all the uppercase, all the lowercase, all the numbers, and then some of the special characters. So does that answer your question? Because there are 26 lowercase, 26 uppercase, so that's 52 right there, plus 10 usual digits. So now we're up to 62. And then we also need plus and slash to mean two specific values somewhere between 0 and 63. So is that okay? Yep. Say again. Base 16 is uppercase or lowercase. I don't think it's case sensitive. With base 16, it is not. But base 64 is case sensitive. So why do we need base 64? Okay, because I think that's the natural question for you guys to ask. Is like, who would use base 64? Even octopi only has 8 limbs when they're not drunk, right? So who would need base 64? Hmm? You want to send binary content over HTTP, which is the Hypertext Transport Protocol. Because HTTP is an ASCII only protocol, which means whenever you make a get or a put request, when you want to get something from a website, what you can specify can only be stuff they can type on the keyboard. Okay, you cannot specify binary stuff. So what if you want to send a picture to upload to the server? Your picture is binary because it's an image file. So you need base64 to convert the binary content of your image file into a base64 format, which becomes a gigantic string, okay, of 0 to 9, 1 to z lowercase, 1 to z uppercase, the plus, and also the slash. That thing would then be once it arrives at the server will go like, okay, I know this is all in base 64, and then convert it back into the binary format. So now you can actually upload your image file to a remote server. So that is the reason why base 64 exists. It is a way for us to specify binary content as efficiently as we can possibly be using an ASCII only protocol in networking. But because this is not a networking class, I'm not going to dwell too much into base 64. But for those of you who are curious, now you know. All right, so getting back to here. Okay, so now the question is, okay, tag, you said that, okay, so how many zeros do we need here? Okay, each base 16 digit specifies 4 bits. The floating point number in double has 64 bits. So how many zeros do I need in order to pad the whole thing so that it ends up with 64 bits? In other words, I know we have at least 1 0 here, but I know I'm missing a whole bunch. How many? Okay, this is specifying 4 bits. We're up to 8, 12, 16, 20. So between these 5, I have 20 bits, and I need 64. So how many zeros do I need to make up for the other 44 zeros in binary? How many hexadecimal zeros do I need for 44 binary zeros? 11. Very good. That is correct. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So now we put the whole thing together. And in C and C++, you can specify 0x as a prefix for a hexadecimal number. And then the rest is really just a copy of all this stuff here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1. There we go. So now I claim that this particular bit pattern specified in hexadecimal, when interpreted as a floating point, a double floating point number, it should specify the value of negative 27.875. So we're going to pause here to make sure everybody understand what I just said. Okay, I'm not, it was a question, okay, but do you understand what the question was asking? And don't ask me to repeat the question because it has evaporated from my mind already. Okay, I can probably paraphrase myself. Okay, the question is, this hexadecimal number is just a convenient way to specify 64 zeros and ones in a particular order. Okay, the question is whether that 64 individual bits in that particular order, when interpreted as a double, specifies the value of negative 27.875. So do we understand that question? So we don't know whether the answer is true or not, okay? But my question is, do we understand what I'm asking? Correct. But only when interpreted as a double. Okay, so now what we'll do is we're gonna play with this bit pattern here and see what's gonna happen. So we need a dumb terminal. Okay, there we go. Here's a dumb terminal. There we go. All right. Oops, that's too big. I think that's probably just right. Okay. So I did this yesterday already for my Tuesday, Thursday class. So I'll just reuse that program. So the program is called, what was it? Oh, I rebooted my computer, so I don't have that program anymore. That's fine. I'll just rewrite it. I'll call it simple. So simple is going to start with pound include standard integer.h, which is a really useful header file because once you have pound included this particular header file, you have access to a bunch of type defs or type definitions that will basically say, when you see this type, it is always going to be 64-bit wide. If you see this one, it's always 32-bit wide, and so on. So we'll go ahead and write the rest of the program. Okay. This is how I usually write programs. I just put in the braces and then go back and backfill things. So this is a uint unsigned integer 64-bit wide underscore t. So when I use this particular type, X is guaranteed to be interpreted unsigned. It is also guaranteed to have exactly 64-bit. So in this class, this is important, okay, because we need to specify how many bits are we talking about. 64, okay? So now I go like x equal to 0, return 0. Okay, that's my entire program. You go like, but this program has nothing to do with what we just talked about. You would expect double to be on it. You would expect the hexadecimal expression to be on it. Nope, none of that. So how do we use this program? GCC-G-O simple.c. This is how I actually compile programs. I don't use VS Code or anything like that. Okay, I just do everything on the command line. GDB is simple. Okay, GDB is the GNU debugger, so it gives me the ability to put a breakpoint. So this time I put a breakpoint on line 6, which is the return 0, and then I just run the program all the way up to line 6. So if I were to ask, hey, what is the value in x? It's a 0. Not surprising, right? So now we can play with it, because now I can say set variable x equals to whatever that hexadecimal representation is. So I'm just going to do a control C on this side and then control shift V on this side, copy and paste, press the enter key, and I say, okay, what is x? That's not negative 27 something. Well, you know that it's not going to be negative 27 something because x is an unsigned integer. It is not capable of representing anything that is negative. Okay? But why exactly is this? Because in this particular bit pattern, we specify we have one of 2 to the power of 63, one of 2 to the power of 62, none of 2 to the power of 61, and so on. That is how this particular value comes. That's why we have this value, because we are interpreting all the bits as an unsigned 64-bit integer. In other words, this is corresponding to VU, open paren F, comma 64. Okay, I hope you guys still remember what is VU. Okay, that's kind of what it is. Hmm? It is the unsigned interpretation of a bit pattern. Yes. Yep. Okay. So maybe we can just kind of typecast it. Nope, that doesn't work either. The reason why it's not working is because what it is casting is this particular value to begin with. The the incorrect interpretation has already happened by the time we get to the double typecast operator. Is that okay? So that's why this approach does not work. Okay, if that is not working, I'm going to try a scenic route. Okay, so the scenic route involves the address of x. So I hope you remember what is ampersand as a unary operator from CISP 360, because after the after week 8 or so, we'll be dealing with addresses and dereferencing a lot. Okay, so if you were not comfortable with pointers and dereferencing in CISP 360, you have about 4 weeks to really catch up with those concepts. Okay, you have been warned. Hmm? Yeah. So pointers are really useful once we get past about week 8 or 9. It becomes super useful. But we're not quite there yet. Okay, so you print this and go like, okay, this particular address, which is in hexadecimal, okay, is the location. This is the location where you can find a unsigned 64-bit integer. Are you surprised? Based on the type of X? No, this is not surprising at all. Are we good so far? Okay. So now we do something with that expression and say, hmm, let's do this. We're typecasting again. But what we're typecasting is not the value. We're typecasting the address. So what is a good analogy to explain what I have just done here? Well, let's just say that, my house is where I live is zoned as a residential area. And I decide, I want to run a little orchard in my backyard because my wife likes to plant stuff. Okay. So I'm deciding that I'm rezoning my parcel code to be an orchard. That is basically what it is. Do I still live at the same place? Yes, but what it is zoned for has just changed from residential, which means yeah, you can live there, you can sleep there, but you better not be producing stuff that you're gonna sell. That's residential, right? So I decided that I'm gonna rezone my parcel code to be an orchard where I can grow stuff and sell that stuff. Okay. So now when people ask, okay, so who is at this address and what can this parcel code do at the address, which is the same thing as dereferencing it. Now, the when the county comes around and they go like, hey, you're selling stuff that you're growing in your backyard. Can you actually do that? And go like, yeah, I'm rezoned as an orchard. This is not residential anymore. We are good. Okay, that is dereference. Okay, so dereference is what is at a particular address, but what is at that address and how you look at the bit pattern at the address is specified by the typecast now. So the typecast is casting the address. In other words, it was the address of an unsigned 64-bit integer, but after the typecast, it became the address of a double. So when you ask what is at the address, which is post casting, then whatever bit pattern, the 64 individual zeros and ones, were no longer interpreted by the VU function. Instead, they were interpreted using the VF function that we talked about at the earlier part of today's lecture. That is how I got back negative 27.875. Is that okay? So as I said, I do not expect you guys to be able to come up with this way to double check and verify the bit pattern is in fact representing negative 27.875. But when I explain the steps, you should understand every step along the way. What is typecasting? What I'm casting, okay? Because I'm not casting the value, I'm casting the address of that location. And then I do a dereference after the address itself is typecasted. So those steps, if you're not comfortable, I would suggest you to kind of catch up, okay? Read about it, okay? Go back to your notes from CISP 360. Well, for those of you who took notes anyway. So it really shows you the importance of taking notes because if you took notes, then you go like, oh, okay, I just have to go back, dig up, probably close to what the last 2 weeks or so in CISP 360, and then read it again, or go back to the textbook, or go online. Okay, you ask Chat GPT, explain typecasting to me. Explain what is the address of operator. Explain to me what is the reference. You guys have way more tools than I ever had, when I was a college student. I'm old enough to say that when I was a college student, the internet did not exist, let alone Google. Okay, the internet itself did not exist. We did have modems and bulletin boards. That's not no. The bulletin boards is kind of like the computer version of CB radio. So if you want to reach a friend who's living in the East Coast, you can do that by having operators in between to relay your message hop by hop by hop all the way to the East Coast. Now, understanding CB radio turns out to be like super helpful if you want to get into computer networking because routers essentially are operators. You have to tell the router this packet has to eventually get to that particular address, and then the router has a little table to go like, oh, so if the packet is designated to the East Coast, this is the port that goes out to the next router along that route. So, you know, it's good to get into networking. Okay, if you have a background in programming, networking is not really difficult. A lot of protocols, a lot of standards, but concept-wise, It is not that difficult. All right. Are there any questions about what we just talked about today? Mm-hmm. Mm-hmm. So yeah, so correct. So if you do something like this, then the typecast is applied to the unsigned interpretation of X already, which is our VU function. So that means, there's nowhere here that actually says anything about VF. Hmm? Correct. Yeah, how you stack it. But uh, if you don't do the cast to the address, there's actually no way to interpret this, the bit pattern, into a double. Right. The only other mechanism to do this is called a union, which is kind of like a companion of a struct. So a struct allows you to specify different members, but all those members exist together in different portions of the memory space of the program. A union, on the other hand, is exactly the opposite. It is you're basically telling the compiler that I can interpret this thing using any one of these interpretations. So I could have used a union to achieve the same thing, but I don't think the concept of a union was introduced in CISP 360 because it's a really obscure concept in C++, and most people do not talk about it. But address of, sorry? Well, we are achieving the same thing, but not using the language construct called a union. Yep, yep. All right. So that's it for the lecture today. Next Monday or so, I will give you a practice exam for exam one, which means 1 week after you have the practice exam, we'll have the actual exam one. Okay. So that means it's going to be at least a week and a half away from today. It is going to be open book and open notes, which also means now would be a good time to start thinking about what you want to bring with you to the exam. It is open book, open notes, but no electronics. So no phones, no computer, no laptop, no tablet. Everything has to be on some form of a dead tree. Yep, everything's going to be on paper. You're going to use pencil or pen to answer the questions. So everything is going to be back to the basics. All right? No logism for the test. That is correct. You won't have access to logism, but you might have questions that has a circuit in it. Yep. So we'll deal with it in the second exam. The first exam does not have anything like that. So before I forget, this is what I'll do. I will give you the exam from the previous semester, just so that you have something to practice on. So let me do that. Go to announcement, add announcement. This is exam one from spring 2025. See attached. Let me go to attachment. That would be here, 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 here. Yeah. And I remember the whole path because it is systematic. What? Yep. So if something is systematic, I can do it. If it's not systematic, like just random digits, I cannot remember anything like that. So anyway, this is the PDF corresponding to exam one from spring semester. Now, if you this is the first time you take classes from me, There are a few things you can count on. One, I never repeat questions. So if you see a question in this exam, it means you are not getting it. Okay. And I usually try to find new ways to test whether you understand the same concepts. So the key is not to overstudy past exams and focus on understanding the fundamentals of what we are talking about. Okay, so I have to tell people that because there are people who over redo exams from the past. I can give you all the past exams, okay, the past 12 years or whatever, okay, and the only thing you can conclude is your exam is not going to be anyone like that. Okay, now is that going to be helpful? Maybe, maybe not. Okay, more practice may be more helpful, but I wouldn't overdo it. Okay, you have to understand the fundamentals. All right, so that's that. And I'll give you the lab for today, which is about borrowing and it's about binary comparison, I think. Okay, so let me scroll to the right one. Yep, it is subtraction and compare. And I'm gonna turn it on and give you the access code. The access code is flags. So this one has to do with the borrow flag, the sign flag, the L flag, and also the overflow flag. So you might want to bring up your notes when we talk about flags or binary comparison. That would be useful. If you do not have the notes with you, you can always rely on my notes, okay, the reading material related to the flags, especially the area that are in a green rectangle. Okay, so when we go to binary comparison, this is the module where you might find material that is useful, particularly things that are in the green rectangles. So if you don't have your notes with you, this is the next best thing you can use, or you can just rely on your memory of the discussion that we have had. Okay, so I think that's it for the lecture portion. Let me stop